Welcome to The Explainer. So today we are unpacking an absolutely wild technological comeback story. Think about the last time your power went out, or, those rising energy bills we're all seeing lately. Powering our world reliably is getting tougher by the minute. But there's this piece of technology born out of MIT that promises to just fundamentally change the entire landscape. We're talking about the story of Ambri. This is a tech spin-off that literally went bankrupt, only to be immediately thrown a lifeline by some of the wealthiest investors on the planet. Let's find out why.
Now, here's the million-dollar, or actually multi-million-dollar question. Back in May of 2024, Ambri filed for Chapter 11 bankruptcy. They cited a really tough fundraising environment and all these hurdles in expanding their manufacturing. And for most startups, that is the end of the road. But almost immediately, their assets were bought out in a court-supervised sale by a massive consortium of lenders. And we're not talking about just any group here. This included Gates Frontier, Bill Gates Fund, as well as Paulson & Co. and a few others. So what makes this specific battery technology so incredibly valuable that these heavy hitters just flat out refuse to let it die?
Okay, let's dive into this. As Ambri's co-founder and CEO David Bradwell put it, they emerged from all that restructuring deeply grateful for the dedication of their team, and they're pivoting away from the business drama to become a leaner, way more capital-efficient organization. They're zeroing right back in on commercializing their third-generation cell product. So to really understand why this billionaire consortium doubled down on Bradwell's team, we need to step out of the boardroom for a second and look at the groundbreaking science that makes this company so unique.
The grid storage problem. To appreciate their solution, we first have to fully wrap our heads around the problem, and it is arguably the biggest bottleneck in the entire green energy transition right now. Wind and solar power are fantastic, obviously, but they suffer from a major flaw: intermittency. The sun doesn't always shine, and the wind doesn't always blow. To integrate these intermittent renewables into our baseload, which is the constant, ultra-reliable power our grid needs 24/7, we have to be able to store the energy when we make it and then discharge it when we actually need it. And we need to do it with a battery that is insanely cheap to manufacture, massively scalable, and practically indestructible. Honestly, that is a notoriously almost impossibly difficult checklist.
Section 2. Inside liquid metal batteries. Honestly, calling this thing just a battery almost does the engineering a disservice. Instead of the solid materials like you'd find in your smartphone, this tech uses an all-liquid construction. According to their foundational MIT research paper, the battery is composed of 3 distinct liquid layers. Up at the top, you've got a liquid lithium negative electrode, right in the middle a molten salt electrolyte, and down at the bottom a liquid antimony lead alloy positive electrode. Now, by using a low-cost metal like lead mixed with antimony, they intentionally keep the raw materials incredibly cheap to source. It completely solves that economic hurdle while keeping a high cell voltage.
But okay, here is the catch, and it's a pretty big one. To keep all those metals and salts in a liquid state, the battery has to operate at extreme temperatures, specifically 500 degrees Celsius. That is hot enough to easily melt lead, and we are nearing the temperature of actual magma here. At first glance, running a battery at 500 degrees sounds like a massive drawback, right? But this extreme operating temperature is actually highly intentional, and it unlocks their biggest design advantage. Because everything inside is molten, it performs what is essentially a physics magic trick. The materials naturally self-segregate by density into those 3 distinct layers. Think about oil and water naturally separating in glass. Because these specific materials are immiscible, which is really just a fancy science word meaning they absolutely refuse to mix, the battery completely eliminates the need for any delicate, complex internal separators or membranes. The negative electrode is totally consumed when it discharges, and then completely reformed on every single cycle. There's literally no physical structure inside to break down or wear out over time.
Section 3. Beating the battery competition.
So we've got this membrane-free, super hot liquid battery. But how does it actually stack up against the conventional batteries we're already using on the power grid? If you put Ambri's liquid metal cell head-to-head with a standard lead-acid battery of the exact same physical size, the volumes are almost identical, right around 11 liters. But looking at the volumetric energy density reveals the liquid metal holds significantly more energy in the exact same space. And check out the bottom row: cycle life to 100% depth of discharge. A lead-acid battery can't even survive 1,000 deep cycles, but the liquid metal battery, it sails past 7,300 cycles. I mean, it's not even a contest. The real heavyweight fight, though, is against lithium-ion, which is the current favorite for grid storage. Lithium-ion carries a very well-known risk of thermal runaway. They can literally catch fire, which means developers have to spend heavily on complex, highly expensive fire control systems. Ambri's liquid metal battery? Inherently safe. It's passed strict safety certifications and simply cannot experience thermal runaway.
Plus, lithium-ion degrades at about 2.6% per year. Liquid metal degrades at less than 0.25%. Because of that fast degradation and the heavy fire risks, the total cost of ownership for a standard lithium-ion system can actually be up to 45% higher.
Section 4. Scaling up visually.
So the lab data and the economics are super compelling. But how do we go from a pool of 500-degree molten metal to something that can actually power a city block? It all starts right here with the fundamental building block. This is a single liquid metal battery cell. It's just an unassuming, fully sealed little block that holds roughly 1 kilowatt-hour of energy capacity. And because there are 0 moving parts and it's completely self-contained, it operates as a perfectly modular unit.
And this illustrates exactly how it grows. They take 32 of those individual cells and wire them all together into a tray. Boom! Now you have a unit capable of about 30 kilowatt-hours. But here is the truly genius part. The heat generated by the normal charge and discharge cycles of these cells, because they're packed so closely together, actually maintains that required 500-degree operating temperature all on its own. The battery functionally heats itself just by doing its job. It's remarkably efficient.
Finally, to reach true grid scale, 40 of those trays are loaded into a standard 20-foot shipping container. This creates a massive, modular 1 megawatt-hour block. And this is the final unit that gets shipped out and deployed to those enormous renewable solar and wind projects. You literally just line these containers up side by side, plug them in, and you instantly have safe, massive grid storage.
Section 5. Real-world proof and future.
Look, it's very easy to get excited about nice 3D renderings and fun theories, but that consortium of billionaires didn't rescue Ambri based on theory. They did it because this is a tested reality. Ambri deployed a prototype pilot system to support a Microsoft data center. Now, data centers have absolutely zero tolerance for power interruptions. They usually rely on highly polluting, dirty diesel generators for backup, which carries huge environmental stakes. This 40 kilowatt-hour clean energy pilot went operational back in September 2022. Over the first 7 months alone, it hit over 350 cycles. But the absolute craziest statistic? The reaction time. It went from completely idle to full power in under 6 milliseconds. That is instantaneous reliability.
And when you look at the raw operational data from that pilot, it reveals these highly stable repeating wave patterns. It shows the battery charging and discharging with just incredible consistency, holding strong at 76% to 87% efficiency. This real-world chart confirms exactly what the founders promised way back at MIT. This technology is completely viable for massive data centers and perfectly capable of eliminating the need for those high-emission backup diesel generators altogether.
But the absolute ultimate proof? It's in the longevity. Look at the blue line on this graph, representing cycle efficiency over time. It is a completely flat line. This data showcases over 2,000 full discharge cycles. That is the equivalent of roughly 7 solid years of typical heavy daily use, and there is absolutely zero capacity fade. None. Because those liquid electrodes reform perfectly on every single cycle, there's no memory effect at all. The battery at year 7 is functionally identical to the battery on day 1.
Which leaves us with this final thought. We know our power grid desperately needs a permanent solution to the intermittency of renewables. We've just seen a piece of tech that dramatically outlasts lithium-ion, completely eliminates the risk of catastrophic fires, and has won the intense financial backing of top tech billionaires even after hitting rock bottom in bankruptcy court. Is liquid metal the ultimate missing link we've been searching for to secure a clean energy baseload? It's a fascinating question, and one thing is for sure. Ambri is a company we all need to be watching very, very closely. Thanks for hanging out with me on this explainer, and I'll catch you next time.